So today I'm going to talk about actions of finite-dimensional Hopf algebras on commutative domains. This is joint work with Pavel Etingof. Some of this work appears in 2 preprints on the archive and also work in preparation. So I'm always working over C for this talk, but maybe some of these results would generalize to positive characteristic. So what exactly are we up to? Oh, so first of all, I'm hoping that this talk is very down to earth. So stop me if you have any questions. I finish when I finish. Yeah, it doesn't matter. All right. Huh? Or, yeah, I have my marker right here. Yeah. All right. So what are we doing? This is a study of quantum symmetry, so I'm definitely on the quantum side of things from a strictly algebraic point of view. But what's classic symmetry? Just as a small motivation, this is all about, well, really old game, taking group actions on polynomial rings or spaces or nice varieties and so on. And this is pretty well understood. So if we wanted to talk about a quantum symmetry, then what will one do? One will make quantum replacements. Okay. So what would replace the role of a group for quantum symmetry? Well, here the best object is really a Hopf algebra. Okay? And what exactly is a Hopf algebra? Well, it's an algebra with multiplication in unit. It's also a co-algebra with co-multiplication and co-unit. And it also has an antipode, which plays a role of an inverse. And of course, there's some compatibility conditions between all 3 of these guys. And I don't want to write them down because it'll take the whole board. So that's a Hopf algebra, but why? Why consider actions of Hopf algebras? Well, these are really considered as the function algebras of so-called quantum groups. They have a nice dual structure, but also Hopf algebras in general are abstractions of 3 guys that we're used to acting with, namely group algebras, universal enveloping algebras, and co-acting with coordinate rings of algebraic groups. So if we understand actions and co-actions of Hopf algebras, then we understand a lot, of course. All right, so we have some choices. I mean, we can't just pick any old Hopf algebra to act with. We should probably narrow down a class to look at. Well, we can choose to act with, let's say, as a C vector space. These guys can be infinite dimensional, which are probably the ones that people mostly act with. But also we can choose the finite dimensional guys, which are still interesting in and of itself. And for this talk, we can consider actions of finite dimensional Hopf algebras. But even among this class of Hopf algebras, there's still a few choices. Okay? So namely, we consider 2 tractable classes of finite dimensional Hopf algebras, namely those that are semisimple, and that's semisimple as a C algebra, and those that are so-called pointed, meaning that all simple H comodules are one-dimensional. Or in other words, H star is basic. All simple H star modules are one-dimensional. So the reason why these are 2 nice tractable classes is because there's a program going on to classify finite dimensional Hopf algebras in these 2 settings. So just to explain a little bit more about these 2 classes of Hopf algebras, because we'll eventually narrow down to these classes, let's just get some examples. Okay? Oh, and by the way, if you have a semi-simple Hopf algebra, that actually implies that it's finite dimensional, which is pretty special to Hopf algebras. Okay. All right, so some examples of semi-simple Hopf algebras include, because we're working over C, group algebras, duals of group algebras, twists of group algebras. This is a twist. A Dreamfield twist that twists the co-multiplication of your group algebra. No. Maybe a finite group. Well, it has to be finite. Finite group. Maybe a dicult cycle twist that twists the multiplication of G. These are all semi-simple. We can get away from groups. There is a non-commutative, non-co-commutative semi-simple Hopf algebra of dimension 8. And then you can get a bunch more semi-simple Hopf algebras by taking extensions along short exact sequences and also smash products. So as one can see, the semi-simple side of things is really group theoretic. Really group theoretic. Yes. So this comes from an extension of groups, an abelian extension of groups. And basically, there's a question of whether you can get all semi-simple Hopf algebras by considering extensions and twists and smash products of other semi-simple group algebras. So, I mean, this is in quotes. This is in quotes. But a lot of theory, the study of semi-simple Hopf algebras is based on, well, it's really analogous to the study of groups. And that's really roughly. I'm saying this really roughly. Okay, but what about the pointed side? Okay, so what are some examples? The main source of examples are Lustig's small quantum groups. And these are finite dimensional Hopf quotients of, well, your big quantum group, U, Q of G. Well, let's say that G is a semi-simple Lie algebra. Okay. All right. Oh, and Q should be a root of unity here. Okay, and you could take variations of these guys to get other pointed finite dimensional Hopf algebras. Okay. So one example that we're going to look at later, I'll actually give the presentation of it, is the Frobenius-Lustig kernel, or the small quantum group UQSL2. Okay. So as you can see on this side of things, I mean, this is pretty Lie theoretic. And again, this is in quotes. Okay. So in fact, there's a really beautiful theorem by Cartier, Cosant, Miller, and Moore that describes Hopf algebras, not necessarily finite dimensional, in the case where H is co-commutative. And it's given as follows. Put this up here. So this is by Cartier, Cosant, Milner, and Moore. And it says the following. If you have H, a Hopf algebra, that's co-commutative. Again, this is over C, or over an algebraically closed field of characteristic 0. And what exactly does this mean? This means that when you apply the co-multiplication and twist, or flip across the tensor product, it's the same thing as applying the co-multiplication. When you have a co-commutative Hopf algebra, this implies that your Hopf algebra is actually isomorphic to the semi-direct product of a group algebra and a universal enveloping algebra, where here your group acts on your Lie algebra G. I mean, that's really beautiful. So your Hopf algebra really does break up into a group and Lie piece in the co-commutative case. Now, as a quick corollary to this, if you were to take H to be finite dimensional and co-commutative, then you actually get that your Hopf algebra is just a group algebra. This is infinite dimensional. And we'll use this later. Okay? All right. So that's what we're going to act with. We're going to act with Hopf algebras. And now we know why. But what exactly are we going to act on? Well, commutative domains, but I'll tell you why. So again, in the study of quantum symmetry, you want to replace the polynomial ring with something nice. You want to replace the polynomial ring with something nice, namely a quantum polynomial ring. Now, I don't know what this is. I mean, this definition is very vague. You have lots of choice. This can be commutative, not commutative, a domain, not a domain. It could be graded, filtered, deformation, quantization. It could be ring theoretically like a polynomial ring. It could be homologically like a polynomial ring. You have lots of choice. But for this talk, for this audience, we take A to be a commutative domain. Okay. All right. So just a wee bit more background about Hopf actions before we get into the results. Because I'm trying to make this talk from scratch. I have to tell you what it means for a Hopf algebra to act on an algebra, what it means for a Hopf algebra to act. So let's just take some more background. Let's just take H to be a Hopf algebra and A to be an algebra in general. Okay? So we say that H acts on A. This happens when A is a left H module algebra. When A is a, well, we have to pick a side, left H module algebra. Okay? Now what that means is, probably the fancy version of this, is that A is an algebra or algebra object in the tensor category of modules over H. That's what this really means. But more concretely, it means that we have 3 bits of information. First of all, we need A to be an H module. Secondly, we need the multiplication map of A to be an H map. So what does that mean exactly? That means that for any H and H with the coproduct of H given like so, say the sum of some tensor products of H1s and H2s, then for any A and B and A, we have that H acts on the product of A and B according to the coproduct of H. Okay? So you have to check this. Secondly, you need the unit, or thirdly, you need the unit of A to be an H map. So what that means is that H acts on the unit of A according to the co-unit of H, or scales by the co-unit of H, for all H and H. Is there a question? Pardon me? I can't hear you. What? Here? No. Where? Here? Here or here? Here. Does the tensor product? You're saying there's a tensor product? No. No, because we multiply them together. So just to be really concrete, if this is multiplication of A, and let's say that this is action of H, then we send A tensor B to AB to H acting on AB, and then we send, the tensor product will be here, and then we multiply them together. Okay? All right. Thank you. All right. So in classic symmetry, there are a lot of nice results about group actions on polynomial rings or varieties when the group action is faithful. When the group action is faithful. So we need a notion of this for Hopf actions, and that's the notion of inner faithfulness. So we have an analog of faithfulness. Okay, so we say that H acts on A interfaithfully. Basically, the action doesn't factor through a smaller quotient Hopf algebra. If the action doesn't factor through a smaller quotient Hopf algebra. So basically what that means is that there doesn't exist a non-zero Hopf ideal of H, so that there's an induced action on this quotient on A. Okay? So if we have a Hopf algebra action, we really want to talk about the Hopf algebra action, not anything smaller like a group acting. Okay? All right. So if we have a Hopf algebra action, then we know lots of things about various structures arising from the Hopf algebra action. So if there exists an H action on A, then we know pretty general results about the invariant ring coming from the H action on A, the smash product algebra coming from the H action on A, which is the analog of a skew group algebra. We know lots of general results. I mean, books have been written on this. But what we really lack is the understanding of examples. When do we have a Hopf algebra action? So the goal is to answer the question, when does H act on A, and probably really importantly, interfaithfully? We have the whole Hopf algebra acting on your algebra. And again, we lack the understanding of examples. We lack the understanding of examples in general. I mean, we have the usual examples of, let's say, a group algebra acting on a polynomial ring where V is a faithful representation of G. Of course, we can take UQ of G acting on this polynomial ring by derivations, and of course, Q versions of this. But if you take a general Hopf algebra, what are its modular algebras? If you take a general algebra, what are the Hopf algebras that act on it? And there are a couple of reasons why we really do lack the understanding of examples. So, first of all, this is dependent on the classification of Hopf algebras to some extent, and as a program that's currently underway. So that's one reason why we really lack the understanding. Secondly, computations can be pretty horrible. So if I have imagine you have an algebra with lots of generators and lots of relations, and you have a Hopf algebra that has a really long coproduct. Imagine checking this condition here. I mean, I've done this. This is not nice. You screw up a sign, you're done, and you get a student to do it or whatever. Computations are really not the way to go. So we really do need more sophisticated techniques to either rule out examples or to classify actions. So that's why this problem is hard. Now, more importantly, why should you care? Why should you care? Well, I guess for this audience, you might want to consider the quasi-classical analog of this problem. So, why care? Again, you might want to consider, I always spell this quasi-classical. What S? One S, two S's, okay. I don't get paid to spell. All right. Okay. So, what's an example of that? Let's take G to be a Poisson algebraic group. I have to mention Poisson, right? I mean, okay. Any bracket you like. Take X to be an irreducible algebraic variety with 0 Poisson bracket. So we can deform OX nicely. And then the question, this question over here, really boils down to, let's determine when G acts on X, and of course classify all such actions. Okay? And this problem can be pretty tough. It also includes the problem of classifying Poisson homogeneous spaces. Okay, where here, X will be just the quotient of G by some G prime, a closed subgroup of G with the induced Poisson structure. Okay, so that's one reason why you should probably care. Are there any questions so far before we get to the results? Yeah, so put 0, Poisson bracket. Oh, you probably can't read that. Yeah. Well, we want to consider faithfulness. I mean, we probably want to impose that. Yeah. So, faithful. Okay. Any other questions? All right. So I'm supposed to tell you that I've done something. So let's let's state some results. And again, we're going to work in the semi-simple and pointed cases, because these are the two most tractable classes. And they're very different from one another. They're very different. So what's really nice about this is I didn't study Hopf algebras in my thesis. It definitely wasn't part of my graduate training, so I've been learning a lot about Hopf algebras, which has really forced me to learn a lot about groups and linear algebras. I mean, I'm trained as a ring theorist. So I think this stuff is a lot of fun. And if there's anybody in the audience who is into Hopf algebras or anything related to this stuff, I will be very happy to talk to you. Okay. Okay, so some results. All right, so first set of results, we're going to restrict to the case where H is semi-simple. Of course, this implies that the Hopf algebra is finite dimensional. And we're going to act on a commutative domain. Okay, so here, the result is easy to state, but the proof is sort of complicated. And in a pointed case, the result is kind of complicated to state, but the techniques are fairly straightforward. So the result is as follows. Okay, so if a semi-simple Hopf algebra, let's say H acts on a commutative domain, say A, interfaithfully, then the Hopf algebra must be isomorphic to a group algebra. Okay? So what this means is that you can't have any honest semi-simple Hopf actions on commutative domains. Okay? Interfaithfully. If you have one, then it must factor through the action of a group. So that non-commutative, non-co-commutative Hopf algebra that I erased, H8, that can't act interfaithfully on a commutative domain. You really must have a group action sneaking around. Okay? So I'm not going to give the proof of this result, but I'll just crudely sketch it. So very crude proof sketch goes as follows. So if H acts on a commutative domain, or H acts on A interfaithfully, then H star coacts interfaithfully. So H star coacts on A interfaithfully. And what this means is that no smaller Hopf subalgebra can coact. And so what we did was we showed that the H star coaction on A actually restricts to a coaction of a commutative Hopf subalgebra we call it H prime. In particular, it's generated by a co-ideal subalgebra, if you care. Okay? So what this means, because of interfaithfulness, this means that H star must be H prime. So this implies that H star is finite dimensional and commutative. So this implies that H is finite dimensional and commutative. And then we're done. Co-commutative, sorry. Co-commutative. And then we're done by that result over there, number 2. Okay? Pardon me? Oh, this step right here? I skipped. I can give you the sketch afterwards. It takes like 5 or 10 minutes and yeah, this is the hard part. Oh my God, I'm starting to sound like my husband. He's from Boston, hot pot. Okay. Integration by Pats. Okay, so this is the hard part. Okay. All right. So what about the pointed case? Again, this is a little more complicated. Because there are lots of actions, and how do we keep track? There's too many actions, which is probably a good thing. Let's see. If you have a group algebra, is it string-field doubles? Is it semi-simple? I believe so. I mean, I want to tell lies. And well, duals. I mean, semi-simplicity is preserved under duals. Yeah. Duals. Yes, I think so. No, it's not. Lie. No. So I don't know. Okay, so now the case where H is finite dimensional and pointed. And again, these are like the Lie type of Hopf algebras. And okay, we're acting on commutative domains. All right. So first of all, this study boils down to the action on fields. So if you look on the archive, you'll see pointed Hopf algebra actions on fields. This is why. And it's due to the following lemma. The study boils down to action on fields. Okay, and it's due to the following lemma, due to Scriabin. I don't want to mispronounce names. Okay. All right. And what it says is that if you have H, a finite dimensional Hopf algebra acting on a commutative domain, interfaithfully, then that implies that H acts on the quotient field interfaithfully. So interfaithful Hopf actions, interfaithful finite dimensional Hopf actions on commutative domains induce interfaithful finite dimensional Hopf actions on fields. So it really boils down to studying Hopf actions on fields. So this prompts the following definition. We say that a Hopf algebra, H, is Gala theoretical, or GT for this talk, if it acts interfaithfully and C linearly on a field containing C. Okay. So, some quick results about the Gala theoretical property. First of all, first result, any finite group algebra is Gala theoretical. Any finite group algebra is Gala theoretical. Secondly, if you have H and it's semi-simple and it happens to be Gala theoretical, that implies what? H is a group algebra. And probably the third property is the most important. When is the Gala theoretical property preserved and when is it not preserved? So thirdly, the Gala theoretical property is preserved undertaking Hopf subalgebras and undertaking tensor products. But it's not preserved undertaking Hopf duals and undertaking twists. Both twists, 2 cocycle and the dual 2 cocycle twists. Okay? All right. So, as before in the general theory, if you have a Hopf action on the algebra, you might be interested in its invariant ring. Or in this case, you might be interested in its subfield of invariance. What about it? What happens? Do we have anything related to Gala theory? We should, because we called it Gala theoretical. And we do. Okay. And we have the following theorem. If you have H, a finite dimensional pointed Gala theoretical Hopf algebra. Okay, so this is going to act interfaithfully on a field. So with H module field L, then the following happens. First of all, what about its subfield of invariance? What does it look like? This actually comes from the action of a nice group algebra contained in H. Oh, hello. This actually comes from the action of the so-called group of group-like elements of H. And what is this? These are all the elements, G and H, so that the coproduct of G is just G tensor G. So basically, you can understand its subfield invariance just by looking at a group action. Moreover, you have that this extension of fields is a Gala extension. Is a Gala extension, with Gala group being this nice group GH. Okay? All right. So we have additional results in this direction where we can replace A with a commutative domain or an Azamaya algebra, and we can even get rid of pointed, and something slightly different happens here. Okay? So at this point, we should do an example. Do an example. So let's take the small quantum group, the Frobenius-Lustig kernel, UQSL2. Okay? And here, Q is going to be a root of unity and the order of Q squared is going to be M. So this guy is going to have dimension M cubed. And you'll see that in a minute. It's generated by 3 elements, E, F, and K. And here are the following relations. So E and F commute like so. K and E commute like so. K and F commute like so. And K to the M is 1. And both E to the M and F to the M are 0. And as far as the coalgebra structure of this small quantum group, we have that K is group-like, and E and F are so-called skew primitive, meaning that you have a very nice co-multiplication. Namely, E is K1 skew primitive, and F is 1 K inverse skew primitive. Okay. So putting this all together, what is the group of group-like elements of H? Where all the group-like elements are really generated by K. So the group of group-like elements is just isomorphic to the cyclic group of order M. And we can see that this field extension is a cyclic extension of degree M. So this is Gala, cyclic, degree M. Okay. All right. So are there any other questions on this part? Pat? Pardon me? L? Oh, shoot. You have to give the action. Ooh, sorry. Good question. All right. So for example, and this is not obvious, we can take L to be this field where K acts on U by Q to the minus 2U, E acts on U by 1, and F acts on U by minus Q U squared. Sorry, thank you. Okay, not completely obvious. Any other questions?
So what is the extra information that you get from the fact that you have an Hopf algebra action instead of just
what is the benefit of, so you don't have any extra information about the invariant ring.
No.
I mean,
So,
but in terms of the Hopf action,
you can describe the field extension the same. You have a cyclic extension of degree m.
yeah, so in terms of this, you don't have any extra information from the Hopf algebra. It strictly comes from the group of group-like elements. Yeah. For this invariant subfield. But if you want to consider like smash product algebras or some other constructions coming from the Hopf algebra action, you might actually have to deal with the Hopf algebra. Okay? Yes?
I don't see the relation f to the n equals 0 in this action.
Here? Yeah. Oh, yeah. I can show you afterwards.
Is there a hint?
You can even, I think it even, f squared might even act as 0. I mean, you have to apply, ooh.
There's some polynomial comes out.
Yeah, and you have to apply the coproduct of h to act, which is a little,
Whack it out. Okay.
yeah.
Take
I think it even works for m equal to 2.
Okay, great.
All right. Okay, so what about classifying all fine-dimensional pointed Hopf algebras that act on commutative domains? This is impossible because the fine-dimensional pointed Hopf algebras aren't classified yet. But they are classified, or they're the most extensively studied, in a case where your Hopf algebra is a so-called finite Cartan type. So I'll tell you what that is, and I'll tell you what we know, and I'll probably run out of time at that point. So I've been reading a lot of these guys' papers, and by these guys I mean Nicholas Andrzejewicz and Hans Schneider. Those are the main two individuals who are leading the program to classify finite-dimensional pointed Hopf algebras. And it's really beautiful stuff. Okay. So we have examples and some classification results. For finite-dimensional pointed Galo-theoretical Hopf algebras of finite Cartan type. Okay, so I'm going to tell you what that is in a theorem and definition. Okay. Okay, so this is due to Nicholas Andrzejewicz and Hans Schneider, and also due to Andrzejewicz's student, former student, Ivan Andriano. And it goes as follows. So if you have H finite dimensional, pointed, and you happen to have that its group of group-like elements is a billion. This is the most understood case. Is a billion. Then you know how H is generated. You know that H is generated by group-like elements. So some G's and G of H. Okay? And you know it's also generated by skew primitive elements. Skew primitive elements. So some xi's where the coproduct of xi is gi tensor xi plus xi tensor 1, where gi is group-like. So you have a very simple co-multiplication or coproduct on your xi's. And we say that H is a finite Cartan type if the gi's and xj's commute according to a Cartan matrix. So in particular, we have that gi's commute with xj's by some scalar qij, where the qij's satisfy the following relations. So qij times qji is QII, AIJ, where AIJ is a Cartan matrix associated to some semi-simple Lie algebra. And here we need the QIIs to not equal 1. So that's it's a bit of a handful. So I'll just show you that UQSL2 is a finite Cartan type. By the way, this QIJ is considered, or it's called the Brady matrix of your Hopf algebra. So as an example, if you take H to be UQSL2 and take G1 and G2 to be K, and X1 and X2, or X1 to be E, and X2 to be KF, because you need it to be K1 skew primitive, then you have the following Brady matrix given by, well, K and E commute by Q squared. And then we have the following entries for the rest of the relations. Okay? So that means that the Cartan matrix associated to this Hopf algebra is just the one of type A1 cross A1. So the small quantum group is a finite Cartan type A1 cross A1. Okay? All right. So really briefly, I'll tell you that we have a bunch of examples and non-examples of Hopf algebras of finite Cartan type that are Gala theoretical. So just say maybe theorem. Other examples include Taft algebras, and these are of type A1. Of course, UQSL2, which is of type A1 cross A1. We have twists. So we have twists of the small quantum groups UQGLN and UQSLN, which are of types A1, AN-1 cross AN-1. And then twists of the positive part of UQ of G, which is of the same type as G. We also have some non-examples too, and some classification results precisely when certain Hopf algebras are Gala theoretical. So I guess I'll end with Hopf algebras have a very complicated structure. It's very hard to tell when they act on an algebra because you have to use the full structure of a Hopf algebra. Computations are nasty, so we need more sophisticated results. And this has application to other fields, obviously. I do know of a few other results for actions on non-commutative domains and also non-domains. But of course, I don't have time to get into that. Thank you all for listening. Yeah. Okay. Oh, what should I pick? That's a problem. That's an open problem. So I know a lot of group actions, but so let's just take something simple like the algebra generated by U and V, where UV plus VU is 0. Okay, that's probably the simplest non-commutative domain. So this Hopf algebra H8 acts on it. I don't want to write down the presentation of it, but it's 8-dimensional, non-commutative, non-commutative, and also the Taft algebras. I mean, basically, this is like the positive part of UQSL2, roughly. That also acts on this guy. And there's actually a conjecture. I mean, there are a lot of actions. But there's actually a conjecture about how to relate the pi degree of H with the pi degree of A. What's the pi degree? Pi degree, when the algebra is module finite over a center, is basically a measure of how far a ring is from being commutative. So like the pi degree of an n by n matrix ring over C is n. So we have a conjecture on how to relate the pi degree of your Hopf algebras with your module algebras in the case where this is module finite over a center. So there are a lot of actions. We don't really have a result yet. Yeah. And that's the case for a lot of these. We have examples, not a lot of results, stuff to do, keep me busy. Yeah. Yes?
In the example where G specifically, do you have that Hopf algebra whenever you have a Cartan matrix, right? Is it uniquely determined in the Cartan matrix?
Pardon me?
So that Hopf algebra over there on that whole, yeah.
Mm-hmm.
So if you're given a Cartan matrix, then it's uniquely determined when you have that Hopf algebra.
No. I mean, you can have, so you can have several different types of Hopf algebras associated to a Cartan matrix.
But of that type,
Of this type, you can still,
without the generative relation to the GIs and the XRAs and the whole product.
well, there's still some freedom on how to choose the Brady matrix. Yeah, still a bit of freedom. Yeah.
And then this one natural X on a certain view, I mean, that's also natural X.
Natural actions, I don't know. Yes, yes. No, not unique. There are probably other fields that, so that's one question to determine when an action happens and then to classify them all. Even if there's an H action, so this H action on L, given like so, there might be another one. But I don't know, yeah. There's a lot of freedom. Yeah.
Yes, let me ask something. Maybe it doesn't make sense from your point of view, but it's motivated by a semi-classical.
Please, yeah, because I'm trying to learn new words.
If you have an action, if you're given the algebra, you have an action. How much of the co-product is determined by the action?
Oh, okay, so you fix an algebra.
Yeah.
You have a Hopf algebra acting on it.
Yeah.
You have a Hopf algebra acting on it. And then what's the
Well,
question? Or
If you prefer, you have just an algebra acting on the algebra.
oh, just an
And
algebra.
Can I make it into an algebra action?
Ooh, yeah.
And what is the freedom that I have in doing that? How much of the action determines the co-product structure?
So yeah, you really do need, well, you need the coproduct. So first of all, you need the, so you're concerned about having a Hopf algebra, but just having the algebra structure of the Hopf algebra acting. And you want to know, when does that algebra structure extend to the action of a Hopf algebra acting? That's tough. I don't know. I mean, besides just checking that it works. Abstractly, you could take the dual.
With some assumptions on the action and the outcome of its action.
Yeah, if you throw enough assumptions at it, it's going to go through.
This is not the kind of question that appears.
Not that I'm aware of. I mean, you can take the dual of the algebra structure of the Hopf algebra. You get a co-algebra, and you can ask, when does that co-act on the algebra? And that, from what I know, is hard to tell. But again, this is something that, yeah, any type of way to cook up Hopf algebra actions from something that we already know is tough, I think. That question made a lot of sense.
Thank you again.
Thank you.